Hello and welcome to my video, lesson 3 and 4.1. So it's chapter 3 and 4 combined from the workbook that I use in my class. But anyways, it's about the basics of exponential functions. So this is just talking about exponential functions for now. The latter half of this unit, this topic, 3 and 4, is talking about logarithms. So they're going to be interconnected shortly, but for now, just exponential functions. So we know a lot of exponent laws from Math 10C. If you don't, I highly recommend you go back and you take a look at those in the top corner here. And you watch some of those videos if you don't remember any of the exponent laws, because it's important to know in order to solve these questions. Okay, so let's dive right in. So the parent function is going to be like this. When we're doing any transformations, it's going to be based off of that. On your formula sheet, we have it written as this. Now, we're going to use this when we're talking about applications a lot in the next video. But for now, let's just talk about the top version. So the top version has these three things. A is the initial amount, B is the rate of growth or decay, and X is the number of compounding periods. So if you have an annual rate of return, let's say really simple here, like I start off with $500. Okay, and then my rate of return is, let's say, 5%. Okay, so that means if it was 1 year and it was an annual rate of return compounding annually, simple interest formula would be like, okay, this is good to go, and we would get our next year. But what we're going to see here is that this is the number of compounding periods. So if it was compounding annually and it was an annual rate of return, and there's 5 years, this goes up to 5 because there's 5 compounding periods. And it changes depending on how many compounding periods you have, and that will also change this number with finances in our next video. So let's keep going in here. So let's take a look at some data tables. Let's just think about this as data tables and then shortly graphs, and then we'll keep going. So here in this question, you can hopefully see that if x is, I'll start with x being 0 here, then what is y? It's 1. Okay, if x is 1, then what is y? It's 2. Then 4, then 8, then 16. Okay, let's go in reverse and call this -1, -2. So what are x and y in those positions? Well, we know that based off our exponent laws, if we have a negative exponent, like this is 2 to the -1, then we flip and we have the reciprocal. So it looks like that, which is 1/2. And you continue this pattern backwards and you get 1/4. And what you can see here is you always double if you're going down the column, and you're always halving when you're going up the column, including to the negatives or from the negatives. So if we're going down, it's always multiplying by 2, and if we're going up, it's always dividing by 2. So this is a pattern that we're looking for if we have some data tables. If it was adding by the same number every time, it's a linear function, but this is multiplying by the same number every time, or dividing, because dividing by 2 is the same as multiplying by 1/2. Okay, so let's take a look at this next one here. Let's, you know what? We're gonna change this one here because I think this is important. There you go. We're gonna change that value before we get there. Okay, so this first one here with 3, hopefully you're gonna notice that. Oh. Well, that screwed it all up, but that's okay. Hopefully you're going to notice that we're going to have 1 here still. And if we have 1, 2, 3, 4, we're going to have 3, 9, 27, 81. So we're multiplying by 3 as we go down the columns, which means if we multiply as we go up, or divide as we go up, we get 1/3, 1/9, and you could keep going. The pattern holds. Okay, looking at this next one, you'll see if x is 0, then it goes 5 times 1/2 to the 0, but the 1/2 to the 0 becomes a 1, so it's really 5 times 1. So if x is 0, the answer is actually 5, because this a value is the initial amount. Okay, if we go to the next one, when we have a 1 here, it's really 5 times 1/2, so 2.5. And we can continue the pattern down, and it's going to get more and more annoying to solve. Three, 1, 2, 5. And then we can go back up the other way. And we get these results. Okay, so the one thing I want you to notice as we graph this is I want you to look at the y-intercepts. And so there's 1, and we're going to do, whoops, another one. And then we'll do the last one in green, 5 times 1/2 to exponent x. So as we look at these different graphs, you can hopefully see that our blue one was this first one here. So this is our blue, this is our red, this is our green. Okay, and hopefully you can see a couple things. There is no y-intercept, right? There's no value, or sorry, x-intercept. There's no value of x that makes y 0. If you look on the y column, it never equals 0. And you can divide by whatever number you want, however many times you want, and you'll never get to 0. So there is no x-intercept. That's why, so there is none. And that's why the asymptote is y cannot equal 0. That's because it will never equal 0. Y will never equal 0. Unless we do a transformation on it, which we'll talk about in a second. Okay, so what about the y-intercept? Well, the y-intercept is the a value, which by default is 1. But in the green answer is 5, because that's when x is 0. And you can hopefully see that again if you look at this graph over here. You can see where the green is hitting the y-axis. It's all the way up here. Okay. The other thing you can maybe see is that the red and blue are basically the same graph, except that the red one grows faster than the blue one, because the rate of growth, the b value, is bigger in red than it is in blue. Now the green answer is a decay rate because it's dropping, as you can see here on the graph. So for all of these, they have a domain of x's in the real numbers, and y is greater than 0. Okay, so we can also do transformations of a parent function, and notice a few things about it. So if there's a transformation, horizontal translation to the left by 4, how do we do this? Well, this just means we replace x with x plus 4. So therefore, it's y equals 3 to the x plus 4. And that will move it 4 to the left. Okay, the horizontal stretch means that we're going to replace x with 2x. So it's going to be y equals 3 to the 2x. And then if we have a horizontal reflection, we're replacing x with negative x, which hopefully you'll notice looks like this to start. But if we have a negative x as an exponent, what that really means is 1 over 3 to the x, because a negative exponent flips and has a reciprocal. Okay, looking at our next one, we have a vertical translation up by 4. So that means y turns into y minus 3. That's the transformation that's occurring. But if you replace y with y minus 3, it looks like this, which we can adjust and change it like this. Okay, back to vertical stretch now. Y is being replaced with y over 6. So y over 6 equals 3 to the x. So when we adjust that, it's going to be y equals 6 times 3 to the x. So actually, when you look at this, you'll notice that a few things. So let's do one more. Let's do one more, actually. Let's do the vertical reflection. So this is y changing into negative y. And so in this case, negative y equals 3 to the x, which means it's negative 1 times 3 to the x. Okay, so you're going to notice, hopefully, a few different things. This, which is a horizontal reflection, is going to be what switches it between a growth rate versus decay. Okay, so whenever you have a horizontal reflection, that's what's happening. Okay, the second thing to notice is right here, the A value which is the initial amount, is based off of the vertical stretch. Okay, so those two things are interesting to notice, yeah, that's transformations. Okay, I hope this video helped you understand some of the basics of exponential functions, and good luck.